In July 2025, a telescope in Chile spotted something extraordinary. A faint point of light moving on a path that didn't belong to our solar system. This was 3I Atlas, an interstellar object on a hyperbolic course, unbound to the Sunday Humanity's third confirmed visitor from beyond the stars, after Oumuamua and Borisov. But soon, astronomers noticed something strange. Behind Atlas, more faint lights began to appear. Small objects, barely visible, moving as if in formation. Not one traveler, but a procession. A swarm. The question is simple, yet unsettling. Are we just seeing cosmic debris, fragments wandering together by chance? Or could this be something more, a coordinated arrival, with purpose we do not yet understand? The story of 3I Atlas begins like many astronomical discoveries with data. On July 2025, the Asteroid Terrestrial Impact Last Alert System, or ATLAS, flagged a point of light moving against the fixed stars. Its automated software calculated the orbit and quickly ruled out anything familiar. The eccentricity, a measure of how stretched an orbit is, wasn't just slightly above one, it was well beyond it. That meant this object wasn't circling the sun at all. It was unbound, on a hyperbolic path through the solar system. The designation came swiftly: 3I Atlas, the third interstellar object ever recorded. Astronomers immediately placed it in context with its predecessors. Oumuamua, in 2017, had confounded researchers with its cigar-like shape and unexplained accelerations. 2I Borisov, in 2019, behaved much more like a classic comet, shedding gas and dust as it neared the Sunday. Atlas, however, seemed both brighter and faster than either of them, with a perihelion scheduled for late October 2025 at speeds exceeding 130 miles per hour. In those first weeks, most assumed it was simply another cometary visitor, rare, yes, but natural. Large telescopes from Hawaii to Chile joined the watch, collecting spectra and photometric curves. The Hubble and James Webb telescopes secured time to capture its chemistry in detail. Everything about Atlas suggested a valuable, if temporary, opportunity to learn about how other star systems form icy bodies. Then came the first anomaly. Survey images didn't just capture Atlas itself, but faint specks near its path. At first, these were dismissed as background stars or noise. But careful follow-up revealed that some of them moved not identically, but suspiciously similar to Atlas's trajectory. Over nights of observation, astronomers began to confirm it. Atlas had company. The physics of this were puzzling. For one interstellar object to appear is already rare. To find others nearby multiplies the improbability. Some suggested that Atlas was fragmenting, perhaps shedding pieces as it warmed under the sun's radiation. Others speculated that the swarm might have been born much earlier, when Atlas was first ejected from its home system. A tidal disruption event, a stellar encounter, or even a violent collision could scatter fragments along similar paths, allowing them to travel together for millions of years before crossing our skies. This natural explanation is both elegant and unsettling. If swarms of fragments are common, then interstellar visitors may not be isolated accidents, but families, cosmic caravans wandering the galaxy. That would mean the number of such encounters could be far higher than we once believed. Yet, the data did not settle the matter. The companions were dim, hard to track, and often disappeared from view. Their spacing seemed unusual, not evenly spread as one might expect from simple fragmentation. Some appeared almost to follow Atlas deliberately, a formation that invited speculation. Scientists remain cautious, framing it as an anomaly rather than an answer. But in the quiet of observatories and the discussions of late-night conferences, the question hangs. What are we really seeing? Just debris, or a design. And so, Chapter 1 of Atlas's story is not about disaster or danger. It is about uncertainty. A single visitor became a group, and in that shift, a mystery was born, one that challenges both our models of interstellar physics and our imagination about what may travel the stars. At first, 3I Atlas appeared to be a solitary wanderer. Its hyperbolic path was plotted, its chemistry analyzed, its speed marveled at. For weeks, astronomers focused their attention on this single object, believing they had time to gather data before it slipped back into the interstellar dark. But as the observations accumulated, something began to emerge at the edges of the images. Tiny points of light, faint, transient, easily dismissed as background stars, seemed to be moving in ways that didn't quite fit the static backdrop of the heavens. The first hints came from wide-field survey telescopes, those instruments designed to capture enormous swaths of sky in rapid succession. Their algorithms are trained to notice anything that shifts between exposures. Usually, the software identifies asteroids, near-Earth objects, or satellites. But in the wake of Atlas, multiple faint candidates appeared. At first, they were ignored, logged as noise or coincidences. It was only when astronomers cross-checked these detections against Atlas's path that the pattern became harder to dismiss. Several of the faint points were not fixed stars at all. They were moving, slowly but surely, along trajectories that mirrored Atlas's own. The natural explanation was fragmentation. Comets and icy bodies are fragile. As they warm, volatile ices turn to gas, creating internal stresses that can split a nucleus into smaller pieces. Such events have been observed many times within our solar system. In 2006, Comet 73P, Schwarzmann-Wachmann 3 broke into dozens of fragments, each trailing behind the parent body like sparks from a firework. If Atlas had shed material during its journey through interstellar space, or more recently under the heat of the sun, its companions might be nothing more than shards of the same original object. Yet the evidence was not so simple. Some of the faint followers appeared too far from Atlas to have broken away recently. Their separation suggested much older origins, perhaps even dating back to the moment Atlas was ejected from its home system. In that case, we may not be looking at fragments at all, but fellow travelers, part of a loose convoy cast adrift together millions or billions of years ago. If so, Atlas is not just a lone messenger, but part of a caravan of debris moving through the galaxy on nearly parallel courses. Astronomers debated the implications. On one hand, swarms of interstellar debris would not be surprising. Planetary systems are violent places. Collisions, gravitational encounters, and tidal forces can easily shatter worlds and scatter fragments into space. Over cosmic time, those fragments might remain loosely associated, crossing star systems as families rather than as isolated bodies. Detecting a cluster in our own solar system would then be a matter of probability and timing, not design. But the arrangement of the trailing lights raised questions. They did not appear spread evenly along a broad arc, as one might expect from simple dispersion. Some seemed clustered, others almost aligned, as if maintaining formation. It could still be coincidence. The human mind is trained to see patterns, even in randomness. Yet the more the images were stacked, the more the faint companions stood out. The possibility of coordination crept into discussions, even if cautiously. Could these objects be moving together by intention, not accident? If so, the swarm might not be debris at all, but devices, probes, or constructs. To leap to that conclusion is risky, and most astronomers avoid it. But it lingers as the unsettling alternative to fragmentation, one that cannot be ruled out with current data. For now, the trailing lights remain just that, faint signals at the edge of our perception, hinting at a story larger than one comet-like visitor. Whether they are pieces of Atlas itself, fragments from long ago, or something far stranger, they mark the first sign that this interstellar encounter is unlike any before. Atlas did not come alone, and whatever follows in its wake forces us to reconsider not only what we are seeing, but what might be traveling the galaxy unseen, just beyond the limits of our instruments. The human brain is a pattern-making machine. From the constellations of ancient sky watchers to the modern hunt for exoplanets, we are wired to connect the dots. Sometimes those patterns are real. Sometimes they are illusions born of chance alignment. And when it comes to the faint companions trailing 3I Atlas, this tension between coincidence and coordination is at the very heart of the mystery. When astronomers first noticed the trailing lights, their instinct was to measure. Using careful astrometry, precise positions recorded night after night, they tracked the motion of each candidate object. If they were truly related to Atlas, their paths would not be random. They would share velocity, direction, and orbital characteristics consistent with a common origin. The results were intriguing. Several of the faint bodies did move in broadly similar ways, with orbital solutions that place them on hyperbolic paths through the solar system. That alone is remarkable. Interstellar objects are rare. To see more than one at once is statistically improbable. But improbable is not impossible. Nature can throw dice in surprising ways, and sometimes low-probability events do occur. Yet the geometry raised eyebrows. Some of the companions appeared staggered, as though spread along an invisible line. Others seemed to cluster, maintaining relatively fixed spacing over days of observation. The motions were not perfectly matched gravitational perturbations. Differences in mass and observational error all play their part, but the overall pattern looked more ordered than chaos should allow. One explanation is fragmentation timing. If Atlas broke apart long ago, the fragments would be distributed along its path in a predictable sequence. Imagine a string of pearls, each bead separated by distance but still tied to the same trajectory. As they traveled together, their positions might mimic deliberate arrangement, when in truth they are just following physics. This has precedent. Cometary breakups in our own solar system often leave trains of fragments that resemble orderly lines across the sky. But another layer complicates the picture. Some of the faint bodies appear slightly offset, not just behind Atlas but beside it. Their spacing suggests a loose formation, not a linear trail. And here, speculation begins. Could such positioning be accidental? Yes. Gravitational nudges from planets, radiation pressure, and subtle initial differences in velocity can create complex dispersions. But could such positioning also be intentional, as if maintaining a coordinated geometry? That possibility cannot be ignored. Astronomy is cautious. Most researchers lean toward coincidence, noting how easy it is to impose meaning on noisy data. The history of the field is filled with examples canals on Mars that turned out to be optical illusions, artificial signals later revealed as natural pulsars, mysterious alignments eventually explained by chance. Extraordinary claims require extraordinary evidence, and so far, the companions of Atlas are faint blurs at the edge of detectability, not ironclad proof of coordination. Still, the mind lingers on the what if. A swarm deliberately arranged would change everything. Spacing could allow coverage, like a sensor network spreading across space. Clustering could indicate units working together, perhaps exchanging mass or energy. Even more unsettling, the very act of maintaining formation over interstellar distances would imply technologies far beyond anything humanity possesses. The truth, for now, remains hidden. The faintness of the companions means observations are scarce and uncertain. Some disappear from view entirely, lost in the noise of the night sky. Others reappear days later, their positions shifting just enough to frustrate clear conclusions. Coincidence still explains the data well enough. Coordination lurks as the provocative alternative, unprovable but haunting. And so the patterns in the sky leave us suspended between two interpretations. If they are mere coincidence, Atlas simply happens to be traveling with debris, a natural convoy born from cosmic violence long ago. If they are coordinated, then we are witnessing something intentional, a swarm that has crossed the void together for reasons unknown. In either case, the lesson is the same. What we see in the heavens is never just light on a detector. It is story, it is speculation, and it is a reminder of how thin the line is between chance and design. When astronomers speak of orbital mechanics, they are talking about one of the most precise sciences we have. Equations, first written by Newton and refined by Einstein, allow us to predict the paths of planets, comets, and spacecraft with astonishing accuracy. A spacecraft launched from Cape Canaveral can thread its way past Mars years later, arriving within minutes of its scheduled time. The same principles govern 3I Atlas and anything that might be trailing in its wake. So the question arises, can debris really stay together on interstellar scales? If Atlas is shedding fragments, or if it was once part of a larger body that broke apart? What stops those pieces from dispersing across light years? The first answer lies in velocity. When an object fragments, the pieces inherit nearly the same motion as the parent. Imagine a dandelion seed head blowing in the wind. Each seed drifts slightly differently, but all are carried in the same direction. On cosmic scales, those small differences add up, but not immediately. A group of fragments could travel together for millions of years before becoming so widely separated that they no longer resemble a swarm. We have evidence for this in our own solar system. Comet Shoemaker-Levy 9 broke apart under Jupiter's gravity in 1992. 2 years later, its fragments struck the giant planet in sequence, each following the same orbital path, like beads on a necklace. The physics was clear. Fragments remain in formation as long as their relative velocities are small compared to their shared motion. The same could hold true for Atlas. But interstellar space introduces complications. Over millions or billions of years, gravitational nudges from passing stars, molecular clouds, or dark matter clumps can perturb trajectories. Radiation pressure from starlight, tiny but relentless, can slowly separate fragments. Cosmic collisions with dust grains at tens of kilometers per second can chip away at surfaces, altering spin and momentum. With so many influences, it seems unlikely that a swarm could remain coherent forever. And yet, the detections near Atlas suggest some degree of coherence remains. If these companions are indeed fragments, then they must have broken away relatively recently on cosmic timescales. Perhaps not centuries, but hundreds of thousands or millions of years ago, recent enough that the swarm still hangs together, loose but recognizable. Here is where speculation enters. If natural forces can only keep fragments grouped for so long, what if the coherence of Atlas's companions is not purely natural? What if they are being guided, even subtly? A civilization with the ability to manipulate trajectories could keep a swarm aligned across distances that nature alone would disperse. Even tiny course corrections, applied consistently over time, would preserve formations that should have unraveled eons ago. Another layer of intrigue comes from their spacing. If the companions were simple debris, we would expect a statistical distribution, some clustered closely, others drifting far ahead or behind. But reports suggest a more structured appearance, with spacing that seems almost deliberate. Physics allows this, but physics alone does not demand it. The mind wonders, are we seeing coincidence sculpted by mathematics, or mathematics nudged by intention? For now, the safe answer is natural fragmentation. Orbital mechanics does allow debris to travel together, at least for a time. The followers of Atlas could be nothing more than cosmic siblings, wandering in loose formation since their violent birth. But the alternative, that coherence has been preserved beyond what physics would normally allow, lingers at the edge of possibility. The sky offers no easy clarity. Telescopes track the motions, computers calculate orbits, and the equations of Newton remain undefeated. But somewhere between the numbers and the faint points of light, a question persists. Are these travelers bound only by the cold laws of gravity, or by choices we do not yet understand? When we imagine space, we often picture emptiness, a vast void, where objects move freely in every direction, but reality is more structured. Just as airplanes follow jet streams and ships once relied on ocean currents, objects in space also trace invisible highways shaped by gravity and motion. To understand why 3i Atlas and its companions might be traveling together, we must first understand the physics of these shared trajectories. Every star in the galaxy moves in orbit around the Milky Way's center, and with it, every comet, planet, and asteroid bound to that star. But not all objects stay bound. Close encounters with giant planets or violent stellar births can eject debris into interstellar space. When that happens, the fragments inherit both the speed and direction of their parent system. Over billions of years, countless such ejecta form a population of galactic wanderers. Most of these objects drift alone, their paths randomized by gravitational nudges. But occasionally, groups share nearly identical velocities, forming loose associations. These are the galactic highways, streams of debris moving together, not because of any intention, but because of common origin. Astronomers have already mapped stellar streams, rivers of stars stripped from dwarf galaxies or clusters, all flowing through the Milky Way together. If stars can travel in coordinated streams, why not the smaller fragments that orbit them? In this sense, the companions of 3i Atlas could be fellow travelers from the same birthplace. Perhaps a planetary system billions of years ago suffered a catastrophic collision, scattering icy fragments outward. Over time, some became separated, but others remained close enough to preserve a shared trajectory. What we are seeing now, in our solar system, might simply be the cosmic equivalent of driftwood carried by the same current across an ocean. The physics supports this. When two objects share nearly identical velocity and direction, their relative motion is slow, even if their absolute speeds are immense. Atlas moves at more than 130, 0 miles per hour relative to the Sun, but a companion moving at 129, 999 miles ph in the same direction will remain nearby for astonishingly long timescales. The faster they move together, the less time gravity has to pull them apart. But this raises a deeper question. If galactic highways are real, might advanced civilizations use them deliberately? Just as ancient sailors learned to navigate by trade winds and currents, a species with interstellar ambitions could send probes or vessels along these pre-existing flows. Doing so would save energy, reducing the cost of travel across vast distances. A swarm of probes released into the right trajectory could remain loosely grouped for millennia, crossing the galaxy like a convoy carried by the tides of space-time. Speculation aside, the presence of such highways has real implications for astronomy. If interstellar objects arrive in swarms, then our chances of detecting them increase. Rather than isolated visitors once every decade, we might expect clusters, each one offering a different glimpse into its origin system. This changes the narrative from rare anomalies to a steady stream of evidence about how other worlds form and die. Still, there are puzzles. Atlas's companions seem unusually well placed for detection, as though timed to arrive when our instruments are ready to notice them. The geometry of their approach, threading between Earth, Mars, and the Sun, feels almost too convenient. Coincidence, perhaps, or choreography, if we allow ourselves to wonder. What we call galactic highways may ultimately be nothing more than physics at scale, rivers of rock and ice pulled by gravity and inertia. Yet, for those watching Atlas and its trailing lights, the metaphor holds power. These objects are not scattered randomly. They move along paths written long before our species ever looked upward. Whether natural debris or something more deliberate, they remind us that space is not chaos, but structure a web of motion connecting every traveler, from stars to comets, across the galaxy's endless sea. When 3i Atlas entered the conversation in July 2025, astronomers instinctively reached for comparison. It was, after all, not the first interstellar visitor we had welcomed. 2 others had come before Oumuamua in 2017 and Borisov in 2019. Each left behind lessons, puzzles, and a framework for interpreting what we see now. Yet the echoes of those earlier encounters only deepen the mystery of Atlas, especially with its suspected swarm. Oumuamua was the first. Its Hawaiian name means scout, and that label proved hauntingly appropriate. Detected by the Pan-STARRS telescope, it was unlike anything in our catalogs. Its brightness varied dramatically, suggesting an elongated shape perhaps 10 times longer than wide, like a cosmic shard. It accelerated slightly as it left the solar system, too much to be explained by gravity alone. No visible outgassing was detected, so cometary activity seemed unlikely. Some proposed exotic physics, like hydrogen ice sublimating invisibly. Others speculated about solar sails, alien probes, or technologies we would struggle to imagine. In the end, no consensus was reached. Oumuamua remained an enigma, a one-time apparition that slipped from our grasp too quickly to solve. Then came Borisov. Discovered by amateur astronomer Gennady Borisov in 2019, it provided a reassuring counterpoint. Unlike Oumuamua, this object behaved exactly like a comet. It grew a coma and tail, outgassed volatiles, and fit comfortably within our understanding of icy bodies. Its chemistry revealed carbon monoxide at levels higher than typical solar system comets, hinting at a colder birthplace, but nothing outside the realm of nature. Borisov was the textbook case, a natural fragment from another star system, wandering into ours, behaving as comets should. And now, Atlas. Faster, brighter, and accompanied perhaps by a swarm. The echoes of Oumuamua and Borisov are clear. From Oumuamua, we learned that not every visitor will conform to expectations. Some may defy categories, challenging us to reconsider what counts as natural. From Borisov, we learned that interstellar comets can be ordinary, their differences lying mostly in detail rather than in kind. Atlas seems to straddle these lessons. Its hyperbolic velocity is even greater than either of its predecessors, suggesting a violent ejection from its home system. Its chemistry, dominated by carbon dioxide instead of water, raises questions about formation environments we have barely modeled. And then there is the possibility of company something neither Oumuamua nor Borisov hinted at. The comparison matters because it sets boundaries on speculation. If all 3 objects were wildly anomalous, we might suspect something extraordinary. If all 3 were entirely mundane, we might dismiss interstellar visitors as unremarkable. Instead, we have a spectrum, one deeply puzzling, one comfortably natural, and one in between, pulling us toward questions we cannot yet answer. Some astronomers argue that Atlas simply expands our sample size. With only 3 confirmed interstellar visitors, diversity is inevitable. Nature produces variety. Some fragments will look strange, others will seem familiar. Perhaps swarms are part of that variety, the natural result of fragmentation before or during interstellar travel. Others counter that the sequence feels too suggestive. First a mystery, then a control, then a combination, as though each visitor builds on the last, telling a story in chapters rather than accidents. The echoes of Oumuamua and Borisov are not just scientific, but psychological. Oumuamua awakened the idea that we might not be alone. Borisov reassured us that we might be. Atlas sits uneasily between those poles, forcing us to consider both possibilities at once. Is the swarm mere debris, a comet family crossing our skies by chance? Or is it something more structured, a pattern that repeats because it is meant to? In the end, the comparisons highlight one truth above all. The universe is not obliged to fit our categories. Each new interstellar visitor may surprise us, may teach us, may unsettle us. Oumuamua taught humility, Borisov offered comfort, and Atlas demands patience. Whether its echoes are coincidence or coordination remains unclear. But one thing is certain: the story of interstellar visitors is only beginning, and each chapter leaves us more aware of how little we truly know. As more faint companions were logged behind 3i Atlas, the debate sharpened. What exactly are we looking at? Are these pieces of Atlas itself, torn away by stresses during its journey? Or are they independent bodies, fellow travelers, that just happen to share its path across the solar system? The answer lies in physics, but the implications stretch into deeper questions of coincidence, probability, and perhaps even purpose. The fragment hypothesis is the most straightforward. Comets are fragile. They are frozen mixtures of ices, dust, and rock, held together loosely like cosmic snowballs. When such an object approaches a star, heat penetrates its surface. Gases trapped within begin to expand, producing jets that can fracture the nucleus. Atlas may simply be breaking apart, shedding small pieces that now trail behind like sparks from a campfire. We have seen this before. Comet Shoemaker-Levy 9 fragmented into more than 20 pieces after a close approach to Jupiter. Other comets, like Schwarzmann-Wachmann 3, have repeatedly split into swarms of fragments that spread along their orbits. From this perspective, the trailing lights are nothing extraordinary. They are Atlas's children, created in our neighborhood of space as solar heating does its work. If true, their motions should gradually diverge over time, spreading into a loose cloud rather than holding steady formations. Astronomers are watching closely for exactly that. Any drift that suggests active fragmentation is ongoing. But the observations do not fully settle the case. Some of the faint companions seem too distant from Atlas to have broken away recently. Their spacing suggests separation long before Atlas entered our solar system, perhaps even in its birth environment. This opens the door to the fellow traveler hypothesis, that Atlas and its companions were launched together from the same parent system billions of years ago. If true, this is extraordinary. It would mean we are witnessing not the disintegration of a single body, but the survival of a convoy of fragments across interstellar space. Ejected in a common event, perhaps the disruption of a planetesimal belt or the violent birth of a new star, these bodies would have drifted together for unimaginable spans of time. Their coherence would not be perfect. Gravity, collisions, and subtle forces would tug them apart. Yet, if their initial velocities were nearly identical, they could remain in loose company across light years, eventually sweeping through our skies in formation. This possibility reframes the swarm as evidence of larger processes in the galaxy. If one convoy exists, there may be countless other families of interstellar objects traveling together, crossing star systems as messengers of distant histories. Our detection of Atlas and its companions may not be unique, but rather the first glimpse of a broader cosmic pattern. And yet, questions remain. Why do these companions seem to cluster rather than disperse? Why do some appear almost aligned rather than scattered along a broad arc? The fragment and fellow traveler hypotheses both allow for chance alignments, but neither demands the apparent order that astronomers have hinted at. This is where speculation steps in. If coordination were at play, if the swarm were being guided, even subtly, then these companions would not be mere fragments or fellow travelers. They would be participants in something more deliberate. Science, of course, prefers caution. The evidence is thin, the objects faint, the uncertainties large. The natural explanations are strong and consistent with what we already know. And yet, the very existence of the swarm challenges assumptions. Until now, each interstellar visitor seemed solitary. Atlas may be showing us that solitude was never the rule, so fragments or fellow travelers. Perhaps both. Perhaps Atlas shed some pieces recently while carrying others across the galaxy for eons. Perhaps swarms are the default, and lone visitors like Oumuamua were the exception. Or perhaps, just perhaps, there is a third answer, one we are not yet ready to see. For now, the trailing lights remain ambiguous, suspended between science and wonder. One of the most natural explanations for the companions of 3i Atlas is the idea of a comet family, a group of fragments born from the breakup of a single larger body. This theory is grounded in well-documented phenomena within our own solar system, where fragile comets often shatter under stress, creating swarms that remain loosely bound for years or even centuries. Comets are not solid rock. They are fragile aggregates of ice, dust, and organics. When heated by a star or torn by a gravitational encounter, they can split apart with surprising ease. Astronomers have witnessed this many times. In 1992, comet Shoemaker-Levy 9 was captured by Jupiter's gravity and broken into over 20 pieces. 2 years later, those fragments slammed into the giant planet in a spectacular chain of impacts, each following the same orbital path. More recently, Comet 73P, Schwarzmann-Wachmann, 3 fragmented into dozens of pieces, scattering bright shards across its orbit like glowing breadcrumbs. In each case, the result was a family, multiple bodies, sharing the same trajectory, spread out over time but clearly related. The comet family theory suggests that Atlas may be undergoing, or may have already undergone, a similar breakup. Its nucleus, stressed by heating or internal pressures, could have fractured, releasing smaller fragments that now trail behind. These fragments, faint and difficult to see, would naturally move along similar paths, creating the swarm-like pattern observed by astronomers. But what makes Atlas unusual is the scale. If the companions are truly part of a family, then the breakup may not have occurred in our solar system at all. Instead, the fragmentation could have taken place long ago, in deep interstellar space, or even in Atlas's parent system before it was ejected. Imagine a planetesimal belt destabilized by a migrating giant planet, sending icy worlds careening into one another. The resulting debris could have been cast out together, remaining loosely associated across millions or billions of years. In this view, Atlas is not just one traveler, but the leading member of an ancient convoy, a family that has survived the hazards of interstellar space to arrive at our doorstep. The idea of such survival is astonishing. Interstellar space is harsh. Radiation, collisions with dust grains, and the constant tug of galactic gravity should gradually disperse any cluster. For fragments to still be traveling together suggests that their initial velocities were nearly identical, minimizing their spread. It also hints that comet families may be more durable than we once thought. Rather than solitary wanderers, many interstellar objects could arrive as groups, their family ties written into the sky. If true, this changes how we think about interstellar visitors. Instead of rare, isolated events, there could be chains of arrivals, swarms of fragments, each carrying different pieces of their parents' history. The chemistry of one fragment may differ from another, revealing varied layers of the original body. Together, they would form a kind of sample set, a distributed record of conditions in a distant system. Atlas and its companions could therefore be the first interstellar family ever detected, a gift of data waiting to be unraveled. Yet the comet family theory also faces challenges. The spacing of Atlas's companions does not always look like random dispersal. Some appear too closely aligned, as though arranged rather than scattered. Others seem offset, not in a simple trail, but in a loose formation. Nature allows for such quirks, but the apparent order leaves room for more speculative interpretations. Still, the family model remains the most parsimonious. It explains the swarm without invoking technology or intention. It fits with known cometary behavior, and it situates Atlas within a broader story not as a solitary scout, but as the remnant of a much larger body, one that fractured long before we ever turned our telescopes skyward. Perhaps that is the true power of the comet family theory. It does not just describe fragments, it tells of ancestry. Atlas and its companions are kin, born of a single event, traveling together across the stars. Their arrival is not coincidence, but consequence. A breakup in deep space, billions of years ago, now writes its story across our night sky. For most astronomers, the companions of 3I Atlas are best explained as fragments, the natural outcome of a breakup. But there is another possibility, one that sits uncomfortably at the border between science and speculation. What if the swarm is not accidental at all? What if these objects are coordinated a fleet, not a family? This is the probe swarm hypothesis, a scenario where Atlas and its companions represent something deliberately engineered. To entertain this idea, we must first look at why swarms make sense from a technological perspective. On Earth, engineers already experiment with distributed systems, small satellites working together in clusters. Swarms of drones can survey landscapes more efficiently than a single aircraft. Constellations of satellites, like those providing global internet service, rely on numbers rather than size to cover the entire planet. The logic is simple: redundancy, resilience, and range. A single probe can fail, but 100 working together ensure the mission continues. If an advanced civilization sought to explore the galaxy, it might use the same principle. Instead of sending one massive craft, it could release a swarm of smaller probes. Each could carry sensors, each could sample different regions, and together they could map environments with far greater efficiency. Such probes could be small enough to evade easy detection, blending into the appearance of natural comets or asteroids. From this perspective, a convoy like Atlas's swarm begins to look less like debris and more like strategy. The spacing of Atlas's companions lends itself to this line of thought. Some appear almost evenly distributed, as though maintaining relative positions. Others seem to cluster in ways that resemble tactical groupings. Natural explanations exist, but the order invites comparison with engineered constellations. To remain in formation over interstellar distances would require active control, tiny corrections applied consistently over millions of years. That idea stretches credibility, yet it also raises the unsettling possibility of technology so advanced it appears indistinguishable from nature. This hypothesis is not without precedent in scientific speculation. Harvard astrophysicist Avi Loeb suggested that Oumuamua's unusual acceleration could have been caused by light sail propulsion, perhaps the remains of alien technology. While most astronomers favored natural explanations, the suggestion broadened the conversation. If Oumuamua could raise the question of artificial origin, then Atlas, with its apparent swarm, makes that question even sharper. Still, evidence matters. So far, no artificial signals have been detected from Atlas or its companions. Radio telescopes listening at the hydrogen line have heard only silence. Their spectra, while unusual, can still be explained by exotic but natural chemistry. Their motions, though curious, remain within the limits of physics. Extraordinary claims require extraordinary evidence, and that evidence has not yet appeared. But consider the implications if it ever did. A swarm would make profound sense as a method of galactic exploration. Thousands of tiny craft, seeded into interstellar space, each carrying a fraction of the mission's knowledge. Together, they could survive where single probes would fail. Some could burn up in atmospheres, some could collide with asteroids, but others would endure. Each encounter would send data home, creating a network of cosmic field stations stretching across the stars. The probe swarm hypothesis remains speculative, but it cannot be dismissed entirely. The very features that make the Atlas swarm puzzling, its coherence, its apparent order, its timing, are also the features that would make sense if it were designed. Natural explanations remain stronger, but the hypothesis keeps the door open to one of the most extraordinary possibilities imaginable: that we are not simply watching debris drift past, but observing the instruments of another intelligence moving deliberately through our solar system. For now, the sky offers no confirmation. The companions remain faint, silent, and ambiguous. Yet the thought lingers. If a fleet were ever to pass through, how different would it look from what we are seeing now? When astronomers speak of seeing, they rarely mean using the human eye. Telescopes gather light across the spectrum from radio waves to X-rays and translate it into data we can interpret. For interstellar objects like 3I Atlas, much of the challenge lies not in what we can see, but in what we cannot. Many of its suspected companions are so faint that they slip below detection thresholds, hidden in what scientists sometimes call radar shadows, places where our instruments are simply not sensitive enough to register their presence. Radar has been one of our most powerful tools for studying small bodies in the solar system. By sending radio waves from Earth and measuring their echoes, we can map the shapes and surfaces of asteroids, sometimes down to astonishing detail. The Arecibo Observatory, before its collapse, revealed craters, ridges, and spin rates on near-Earth asteroids millions of kilometers away. But radar works best on nearby targets. For objects far out in interplanetary space, let alone interstellar visitors, the signals fade to whispers too faint to interpret. Atlas itself is bright enough to track optically, but if its companions are smaller, darker, or less active, they may evade radar altogether. Imagine a swarm of icy bodies, only tens of meters across, darkened by cosmic radiation, reflecting little light. They would be nearly invisible, their presence betrayed only when they briefly cross a star in the background or scatter sunlight faintly toward Earth. In this way, the swarm may be larger than we realize, most of its members simply hidden in the radar shadows. This is not speculation alone. We know from our own solar system that most small bodies escape detection. The asteroid belt contains millions of rocks, but we have cataloged only a fraction. Even near-Earth space, crisscrossed by dedicated surveys, likely holds thousands of undetected objects capable of striking our planet. If our instruments miss nearby neighbors, how many more slip past when they arrive from another star? The radar shadow problem also complicates the debate over Atlas's nature. If we can only see the largest or most reflective fragments, we may be underestimating the true scale of the swarm. What appears as a handful of companions could in fact be dozens, even hundreds, moving invisibly in formation. Their faintness does not mean they are absent, only that our technology is not yet equal to the task. And here the speculative question arises. What if the faintness is intentional? A natural object reflects according to its composition and structure. But a probe, if such things exist, might be designed to minimize its visibility, absorbing rather than reflecting radar and light. To us, it would appear as a whisper in the data, a fleeting shadow on a detector, almost indistinguishable from noise. The possibility remains remote, but it underscores how easily the line between natural invisibility and deliberate concealment can blur. For astronomers, the practical approach is to acknowledge the limits. Wide-field surveys like Pan-STARRS and the Vera Rubin Observatory provide the best chance to catch faint companions, not radar. By stacking images and tracking motion against the star field, researchers can reveal objects far below individual exposure thresholds. Even so, gaps remain. The radar shadows persist, filled with the unknown. The lesson is humbling. Our instruments, as powerful as they are, see only part of reality. Most of the cosmos remains hidden, whether by distance, faintness, or deliberate design. Atlas and its companions remind us that absence of evidence is not evidence of absence. The swarm may be larger, denser, or stranger than what our detectors reveal, and somewhere in those shadows may lie the key to whether we are watching a cometary family or something far more deliberate. Before we consider extraordinary explanations for the companions of 3I Atlas, it helps to step back and ask a simpler question. Do swarms matter in nature? The answer is yes, profoundly. From the largest asteroid families to the tiniest grains that create meteor showers, swarms are a natural feature of cosmic dynamics. They tell stories of violent origins, hidden processes, and the fragility of celestial bodies. Consider the asteroid belt between Mars and Jupiter. It is not a uniform scatter of objects, but a structure filled with families. These families are groups of asteroids that share similar orbital elements, inclination, eccentricity, and semi-major axis, pointing to a common origin. Most were born when a larger parent body was shattered by a collision. Over millions of years, gravitational tugs from Jupiter and subtle forces like the Yarkovsky effect, tiny shifts caused by sunlight, heating and re-radiating off surfaces, spread them out, but their kinship remains recognizable. Astronomers can trace these lineages, linking scattered rocks across vast distances back to single catastrophic events. On smaller scales, comets provide another example. Their fragile nuclei often fracture as they approach the sunday. Sometimes the pieces drift apart gently, trailing like sparks behind a firework. Other times, they separate violently, creating cascades of debris that stretch for millions of kilometers. These comet families don't last forever. Solar radiation pressure, planetary encounters, and internal stresses eventually disperse them. Yet, for years or even decades, they remain cohesive, traveling together as swarms that can be observed from Earth. Meteoroid streams provide perhaps the most familiar evidence of swarms. Every August, the Perseid meteor shower graces our skies. Each streak of light is a grain of dust, no larger than a pebble, burning as it enters Earth's atmosphere. All of them come from the same source. Comet Swift-Tuttle, which sheds material on its orbit. Over centuries, that material has stretched into a long, thin stream, but it still travels as a collective, a swarm of tiny particles crossing Earth's path once a year. Other showers, the Leonids, the Geminids, the Quadrantids, follow the same principle. To the casual observer, they are fleeting lights. To astronomers, they are the fingerprints of swarming debris. These examples matter because they demonstrate that swarms are not anomalies, they are the rule. Whenever a celestial body is stressed, fractured, or disrupted, swarming is the natural consequence. In this context, the companions of 3I Atlas may simply be another case of the universe following familiar patterns, even on interstellar scales. A breakup in a distant system could easily create a convoy of fragments, and if their velocities were nearly identical, they would remain together across unimaginable distances. Yet, swarms also raise deeper questions. They preserve history. Each fragment carries slightly different chemistry, different layers of its parent body, frozen records of conditions billions of years old. To study a swarm is to reconstruct a story of collisions, of planetary migrations, of ancient violence. Swarms give us more than one data point. They give us context. In this sense, the Atlas swarm is not just a curiosity, but an opportunity. If we can analyze its companions, we may glimpse multiple pieces of a foreign world, not just one, and still, speculation lingers. Natural swarms are expected to disperse, their order unraveling over time. If Atlas's companions show more coherence than physics predicts, then something unusual is at play. But even if entirely natural, they remind us that the cosmos is rarely neat or solitary. Objects travel together, shaped by the same forces, marked by the same events. To see Atlas with company is not to witness impossibility, it is to witness one of nature's most common strategies, that in the violence of space, when bodies break apart, they do not vanish. They multiply, and they travel as swarms. So far, we have considered swarms as natural. Fragments of comets, families of asteroids, or streams of meteoroids. But in theory, swarms could also arise through design. For decades, scientists and futurists have speculated that an advanced civilization might use swarms of objects, not random debris, but coordinated machines or structures as tools for exploration, communication, or energy harvesting. When we look at 3I Atlas and its possible companions, it is worth remembering that swarms are not just natural phenomena. They also occupy the imagination of engineers. One of the most famous ideas is the Dyson swarm, first proposed in 1960 by physicist Freeman Dyson. He reasoned that a civilization far older and more advanced than ours would eventually need enormous amounts of energy. Instead of building a single megastructure around their star, such a civilization might construct countless small satellites in orbit, each capturing a fraction of the star's light. Together, these satellites, sometimes called Dyson dust, would act like a swarm, encircling the star and collecting nearly all its energy. Unlike a rigid Dyson sphere, which is physically impossible, a Dyson swarm is mechanically plausible. Many small parts, working in concert, could achieve what no single monolith could. The principle here is redundancy and scalability. Swarms can be expanded gradually, repaired piece by piece, and reconfigured as needed. They offer resilience. If one unit fails, the system continues. This logic extends beyond energy harvesting. Swarms of autonomous probes could map entire solar systems, each sampling a different region. Swarms of small craft could communicate across interstellar distances by relaying signals like a cosmic mesh network. In each case, the strength lies not in one giant machine, but in numbers. Applied to 3I Atlas, this raises a provocative question. If swarms are efficient strategies for us, could they not also be for others? Perhaps what looks like a cometary family is instead a coordinated fleet. The companions trailing Atlas could be probes disguised as natural fragments, each carrying instruments, each contributing to a larger mission. From our perspective, they appear as faint specks, but from theirs, they could be a network, a system designed to endure the hazards of interstellar travel. To be clear, there is no evidence yet to support this idea. The chemistry observed in Atlas, especially its carbon dioxide dominance, fits natural models, however unusual. The companions remain faint and ambiguous, consistent with fragments. But the swarm hypothesis lingers because it overlaps so neatly with what we imagine ourselves doing. If humanity ever launches star probes, they are unlikely to be massive ships. More likely, they will be small, cheap, self-replicating craft sent in vast numbers. Swarms will be our solution to the scale of the galaxy. If that logic holds universally, then other civilizations might think the same way. The difficulty lies in distinguishing natural swarms from engineered ones. Both would look like clusters of small objects moving together. Both would reflect sunlight. Both might outgas volatiles. Both would drift along hyperbolic paths. Unless an engineered swarm emitted signals or displayed unnatural maneuvers, it would be nearly impossible to prove intention. In that sense, a probe swarm would hide in plain sight, masquerading as the very comets and fragments we already expect. This overlap between nature and engineering blurs the line of interpretation. A swarm of debris from a distant star system tells us about cosmic violence. A swarm of probes tells us about intelligence. But to our telescopes, the difference may be subtle, even invisible. The only way to know would be to look more closely, to send missions to intercept and sample. Until then, we are left with theory, with possibility, and with the quiet recognition that swarms, natural or artificial, are the most efficient way for matter, energy, and information to move through the cosmos. So when we look at 3I Atlas and its faint companions, we must hold both truths in mind. They may be debris, fragments scattered by ancient collisions, or they may be something more deliberate, echoes of a strategy we ourselves may one day adopt. The universe does not tell us which, it only presents the pattern and leaves us to wonder. When astronomers discuss the possibility of artificial origin, they tread carefully. Natural explanations are always preferred, because nature produces complexity that often masquerades as design. Yet there are moments when patterns emerge that seem harder to dismiss when the arrangement of objects, their spacing or timing, hints at a logic beyond randomness. For 3I Atlas and its faint companions, this is where the debate becomes most delicate. Could the swarm carry the signature of intelligence? The first clue to consider is spacing. In natural fragmentations, debris tends to spread unevenly. Some pieces stay close, others drift far, and over time their separations widen chaotically. Comet families in our solar system demonstrate this. A string of fragments may form after a breakup, but the pearls on the string are rarely uniform. They clump, disperse, and eventually blur into randomness. If Atlas's companions were born from such a breakup, we would expect the same. Yet reports from wide-field surveys suggest something different. A handful of faint objects seem to trail Atlas at roughly similar distances, like beads separated by deliberate intervals. The statistical sample is too small to draw firm conclusions, but the impression is striking. Equal spacing, in engineering terms, is efficient. Satellites in Earth orbit are often deployed in regular intervals to maximize coverage. Constellations like GPS depend on carefully arranged geometry. If Atlas's swarm maintains such spacing over time, it would raise a question. Is this coincidence or coordination? The second clue is timing. Nature is not shy about coincidences. Meteor showers occur when Earth happens to cross a stream of cometary debris, an event predictable but still arbitrary in cosmic scale. Collisions, resonances, and alignments often look meaningful when they are simply the outcome of mechanics. But timing can also be intentional. If a swarm were designed to pass through our solar system during a particular window when Earth, Mars, and our telescopes are in favorable positions, then the encounter could be purposeful. The geometry of Atlas's approach is tantalizing. Its closest approach to the Sun coincides with a moment when Earth is directly opposite, making the object invisible for weeks. By the time it re-emerges, instruments will scramble to catch the last glimpses before it fades away. Some astronomers call this mere bad luck. Others wonder if concealment could be part of the design. Patterns of spacing and timing are exactly the kind of subtle signals SETI researchers have learned to watch for. In radio astronomy, scientists search not for noise, but for narrowband frequencies unlikely to occur naturally. In pulsar studies, they distinguish between chaotic bursts and repeating cycles. The difference between natural and artificial often lies not in what is seen, but in the order behind it. Of course, skepticism is essential. Human beings are prone to seeing intention where none exists. Constellations are cultural, not cosmic. The canals of Mars were illusions of the eye. The wow signal may have been nothing more than terrestrial interference. The risk of overinterpretation is real. Yet, dismissing every pattern as coincidence also blinds us to possibilities. If an intelligence wanted to leave its mark, subtlety might be its method patterns so faint they demand careful attention, but so distinct they cannot be dismissed. In the case of 3i Atlas, the jury is still out. The faint companions may scatter into randomness as more data arrives, proving them fragments after all. But if the spacing holds, if the timing remains uncanny, then the hypothesis of coordination gains weight. Spacing and timing, after all, are not just the language of engineering. They are the language of intention. And so, as telescopes trace the faint lights behind Atlas, astronomers keep two interpretations alive: a natural swarm shaped by fragmentation, or a designed convoy moving with purpose. Either way, the signature is compelling. In space, nothing speaks more clearly than order, and in the silence of the cosmos, even order itself can feel like a message. When people think of messages from the stars, they imagine radio signals, a beam of energy pulsing across space, carrying words or codes. SETI has spent decades listening for such signals, scanning the sky for narrowband transmissions that stand out from the natural static of the cosmos. But communication need not be limited to radio. Motion itself can be language. Patterns written into trajectories, spacing, or timing could serve as messages, visible not through sound but through geometry. This idea may sound abstract, but it is grounded in precedent. Human beings already use celestial motion to convey meaning. Satellites orbit in precise constellations, their spacing carefully chosen to ensure coverage. The timing of their transits encodes intent. GPS satellites pass overhead in a predictable rhythm, providing positioning data to anyone with a receiver. To an external observer, Earth's artificial satellite network would look very different from a random scattering of debris. The order would speak for itself. So what about 3i Atlas and its companions? If the faint swarm trailing behind it were natural, we would expect their trajectories to diverge chaotically, with fragments spreading over time. But what if their motions were not only coherent, but patterned? Could their very arrangement be a form of signal? Imagine, for instance, a sequence of bodies spaced at ratios that reflect mathematical constants, 1, 2, 3, or distances that mirror the digits of pi. Such order would be difficult to explain through physics alone. Or consider timing. If the companions crossed Earth's orbit at intervals that formed a repeating sequence, it would resemble a cosmic code written in the language of motion. Even more subtle patterns could be imagined, such as alignments that recur on exact dates, or geometries that trace recognizable shapes when plotted against the stars. Astronomers have toyed with similar concepts before. Some suggest that an advanced civilization might use pulsars as navigational beacons, their regular pulses forming a galactic positioning system. Others propose that megastructures orbiting stars' partial Dyson swarms could modulate light in patterns detectable across light years. These ideas share a common theme, that messages need not travel as signals in the electromagnetic spectrum. They can be written in patterns of matter and energy, visible to any observer who knows how to look. Skeptics, of course, remind us of nature's ability to mimic order. Orbital resonances can produce elegant ratios without intelligence. Saturn's moons fall into mathematical harmonies that look almost designed, yet are purely the outcome of gravitational physics. Meteor showers repeat annually with clockwork precision, but their timing comes only from Earth's own orbit crossing debris streams. The cosmos is filled with accidental symmetries that tempt us to assign meaning where none exists. And yet, the possibility remains tantalizing. If a civilization wanted to send a universal message, geometry would be a powerful choice. Numbers, ratios, and trajectories are not bound to language or biology. They are mathematics made visible, accessible to any mind capable of observing the sky. A fleet of probes traveling together could thus serve dual purposes: exploration for the builders and communication for the watchers. The very act of arriving in a swarm, rather than singly, could itself be the message: we are here, and we are organized. For now, 3I Atlas's companions remain too faint to reveal such detail. Their spacing may yet prove irregular, their timing unremarkable, their order illusory. But the hypothesis cannot be fully dismissed. As telescopes sharpen their watch, astronomers remain aware of the possibility that motion itself could carry meaning. Perhaps the cosmos does not whisper in radio waves alone. Perhaps it writes in trajectories, using swarms of objects as punctuation marks in the grammar of space. And perhaps, just perhaps, Atlas is not only a visitor, but a message waiting to be read. Every interstellar object that enters our solar system does so on a trajectory written long before human beings existed. Their paths are not chosen in real time, but determined by the physics of ejection from their parent stars and the gravitational pulls they encounter along the way. Yet sometimes, these paths intersect with places that seem almost too symbolic. For 3I Atlas, that place is Mars. Calculations show that in early October 2025, Atlas will pass within roughly 29 million kilometers of the red planet. In astronomical terms, that is closer than the distance between Mars and its outer moon. Deimos multiplied by 1,000. For comparison, many comets pass Earth at far greater distances and still attract intense interest. To have an interstellar visitor come this near to one of our planetary neighbors is remarkable. The Mars flyby matters because of the instruments already stationed there. Unlike the lonely void of most of interplanetary space, Mars is heavily observed. Orbiters, like NASA's Mars Reconnaissance Orbiter, with its powerful high-rise camera, ESA's Trace Gas Orbiter, and even surface rovers have instruments capable of detecting changes in the Martian sky. Together, they form a network of sensors that might catch glimpses of Atlas or its companions from a vantage point unavailable to Earth. This geometry is both gift and frustration. From Earth, Atlas will be near the Sun at the time of closest approach, effectively invisible in the glare. But from Mars, the alignment is different. Observers on or around the red planet may have the best seat in the solar system to witness this passage. For scientists, this creates an unusual opportunity. A chance to study an interstellar visitor not from Earth's perspective, but through the lens of another world. If Atlas is truly accompanied by a swarm, Mars becomes even more critical. Smaller companions may be easier to detect against the thinner Martian sky. A well-timed observation could capture multiple faint objects moving together, offering direct confirmation of what Earth-based telescopes have only hinted at. In effect, Mars could become humanity's remote outpost for studying the swarm, a cosmic coincidence of timing and placement. Speculation arises from this coincidence. Was it truly random that Atlas's path threads so near Mars at precisely the moment when we have a fleet of machines waiting to watch? Statistically, the answer must be yes. Interstellar trajectories are not adjusted to favor our curiosity, and yet the geometry feels uncanny. A convoy of interstellar travelers, passing within observational reach of our robotic scouts, almost as though presenting themselves for study. Coincidence, of course, but a coincidence that tempts the imagination. The Mars connection also echoes older ideas in astrobiology. Some researchers have long wondered whether Mars might serve as a kind of listening post, a place where signals or visitors could be intercepted more easily than on Earth. Its thin atmosphere, lack of oceans, and exposed geology make it a simpler stage for detection. To have Atlas's swarm sweep so close amplifies those speculations, not because of evidence but because of timing. In science, geometry often guides interpretation. Even if no signals or extraordinary phenomena are found, the Mars flyby will still be a triumph of observation. Interstellar objects are fleeting. Their windows of visibility close in months, sometimes weeks. To capture one from multiple vantage points within the same solar system is unprecedented. The data gathered from Earth and Mars together could transform our understanding of how such objects behave. And if, by chance, the swarm reveals itself more clearly near Mars, if the trailing companions become undeniable in Martian skies, then October 2025 will mark more than a scientific milestone. It will mark the moment when humanity's outposts beyond Earth confirmed that our solar system was not visited by one traveler, but by many. When astronomers first began to suspect that 3I Atlas was not traveling alone, one interpretation quickly rose above the rest. Perhaps the companions were simply fragments, drifting debris following similar paths. But another, more unsettling possibility lingers in the background. If the swarm is not random, if the objects are not merely shards of a breakup, then what are they doing? One answer, speculative but logical, is that they are mapping. To map a solar system is no small feat. Even our own efforts have taken decades. The Voyager probes, launched in the 1970s, have spent nearly half a century exploring the outer planets, and still they represent only 2 data points in an ocean of unknowns. Mapping with single spacecraft is slow, fragile, and vulnerable to failure. But mapping with many with a swarm is a strategy that scales. Each unit can take a slice of the puzzle, and together the group can build a far more complete picture. In nature, mapping is unnecessary. Fragments of comets and asteroids do not record data, they simply move. But in engineering, mapping is central. Satellites around Earth constantly map our surface, our weather, our oceans. Constellations of them work together, dividing the globe into coverage zones. If you were an external observer watching Earth from afar, you would see order in the way our satellites move, and you might suspect their purpose. Could the same be true of Atlas's swarm? The geometry of its path encourages such speculation. The convoy does not cut straight through the solar system in a careless line. Instead, it threads between Earth and Mars, swings near Jupiter, and exits toward the outer planets, a trajectory that provides multiple vantage points. If you wanted to survey the architecture of our solar system, this would be a useful route. Each planet encountered would alter the view, offering gravitational assists and fresh opportunities to observe. Even the companions' spread may be significant. If some trail behind, others beside, they collectively sample different regions of space. From one position, Earth might be in view. From another, Jupiter's magnetosphere. From another, the thin dust of the asteroid belt. Taken together, the swarm could provide a distributed map, each fragment acting as a sensor. To us, they appear as faint points of light. To themselves, if they are indeed probes, they might be gathering the first interstellar survey of our home. Of course, the simplest explanation is still natural. A swarm of fragments will naturally fan out, each piece following slightly different paths. By chance alone, some may sweep closer to planets, others farther. That does not make them scouts, only shards obeying the equations of orbital mechanics. But the appearance of coverage, the way the swarm seems to spread its net across multiple planetary domains, is difficult to ignore. This possibility connects to broader debates within SETI. If an advanced civilization were to explore the galaxy, how would it do so? Large starships are inefficient, requiring enormous resources. Swarms of small probes, launched in bulk, make far more sense. Each would be expendable, yet together they would achieve redundancy. Some might fail, but enough would survive to carry out the mission. And what better mission than mapping the collection of information about planetary systems, their chemistry, their architecture, and perhaps even their inhabitants. For now, the idea that Atlas's companions are mapping our solar system remains speculation. The faint objects have not revealed instruments, signals, or maneuvers. They may be nothing more than ice and dust. But the geometry of their passage, the spread of their positions, and the echoes of strategies we ourselves already use make the hypothesis difficult to dismiss entirely. If they are mapping, then we are being studied, quietly and efficiently, by travelers who may never announce themselves. And if they are not, if they are just debris, then the illusion of mapping reminds us of how thin the line is between chance and design. Either way, as Atlas and its companions sweep past, we are left with the same haunting thought. The sky is not empty, and sometimes its visitors arrive not alone, but as watchers. If the faint companions trailing Three-Eye Atlas are truly fragments of the same body, then their chemistry should provide the key to unlocking their origin. Chemistry is, in many ways, the fingerprint of a celestial object. The ratios of ices, dust, and gases reveal where a body formed, how it evolved, and what processes have shaped it. For Atlas itself, the chemistry has already proven baffling. Carbon dioxide dominates its outgassing at levels almost 8 times higher than water, an inversion of what we see in comets of our own solar system. Do the followers share this same strange signature? The problem is one of detection. Atlas is bright enough for the Hubble Space Telescope, the James Webb Space Telescope, and a fleet of ground-based observatories to measure its spectrum. But the smaller companions are faint, diffuse, and easily lost in background noise. Even stacking exposures and applying advanced filtering, most remain little more than smudges on the sky. Direct spectroscopic analysis is nearly impossible with current instruments. For now, astronomers must work with indirect clues. One such clue is coma morphology, the faint shrouds of gas and dust that surround active bodies. Atlas itself displays a wide, extended carbon dioxide coma, stretching hundreds of thousands of kilometers. If its companions are truly fragments, even small ones should sublimate in similar ways, producing miniature versions of the same halo. Some survey images have hinted at faint glows around the trailing objects, but the evidence is ambiguous. Atmospheric distortion, background stars, and instrumental artifacts can easily mimic such features. Another clue lies in photometry, the brightness and color of the companions. Atlas shows unusual reflectivity, brighter than expected for its estimated size, which could suggest a surface rich in volatile ices. If the companions display similar colors and magnitudes relative to their size, it would support the fragmentation hypothesis. If they differ significantly, it might imply that they are independent bodies, only coincidentally traveling nearby. Early measurements suggest at least some color similarity, but the uncertainties are wide. The chemistry question also opens the door to broader speculation. If the companions do not match Atlas, then they may not be fragments at all, but fellow travelers from the same region of space. In that case, their different compositions could represent a cross-section of their birthplace, some richer in water, others in carbon dioxide, others still in exotic volatiles rarely seen in our system. In effect, the swarm could be delivering a chemical survey of its home environment, spread across multiple bodies rather than one. And here, as always, lurks the more speculative interpretation. If the companion's chemistry differs in precise, systematic ways, could that difference itself be intentional? Ratios of gases, chosen and encoded, could function as a form of chemical signaling. We have seen this idea before in theories of extraterrestrial communication, that messages might be hidden in proportions of isotopes, or in spectral fingerprints that stand out as non-natural. In this light, the swarm could be more than a convoy. It could be a message written in chemistry, waiting to be decoded. For now, though, humility is required. The data are sparse. The companions are faint. the chemistry remains speculative. Most astronomers favor the simplest explanation, that the followers, if they are fragments, will share Atlas's bizarre carbon dioxide dominance. If confirmed, this would strengthen the case for a single parent body, shattered either long ago or more recently under solar heating. But the possibility of difference keeps the question alive. Matching chemistry would confirm kinship. Divergent chemistry would imply companionship of another kind, not fragments, but neighbors, perhaps even collaborators, swept together across interstellar space. In the end, the chemistry of the followers is a riddle hidden in faint light. Do they echo Atlas's strange song, or do they sing variations of their own? Until instruments sharpen, the answer remains in the dark. But if we could hear their spectra clearly, perhaps we would discover not only whether they match Atlas, but whether they match each other, and in doing so, reveal the true nature of the swarm. Among the many puzzles presented by 3I Atlas, none has been more striking than its chemistry. Early spectroscopic observations from the James Webb Space Telescope revealed a coma dominated by carbon dioxide, a ratio nearly 8 times higher than water. In our solar system, this is inverted. Water usually makes up the bulk of cometary activity, with carbon dioxide playing a secondary role. Even in water-poor comets, CO2 rarely exceeds water in abundance. And yet here was Atlas, flaunting a chemistry unlike anything we had seen before. The question now is whether its faint companions share the same signature. On the surface, the logic is straightforward. If the swarm consists of fragments from Atlas itself, then the composition of those fragments should match. Each would release gas in similar proportions as they warmed, trailing miniature carbon dioxide halos behind them. A cluster of objects exhaling the same alien chemistry would be compelling evidence for a shared parent body. But nature is rarely so neat. Even within our own comets, chemistry can vary dramatically across a nucleus. One region may be rich in water ice, another in carbon monoxide, another in carbon dioxide. Sublimation depends not only on composition but also on sunlight angle, surface porosity, and internal structure. If Atlas fractured long ago, its pieces may represent different layers of its body, the chemical equivalent of cutting into a cake and finding different flavors inside. Some fragments might be CO2 heavy, while others could outgas water or even more exotic volatiles. This variability is scientifically thrilling. It would allow astronomers to piece together a three-dimensional portrait of Atlas's composition, something impossible from a single body. Each fragment would be a sample, exposing layers that might otherwise remain hidden. If the swarm can be studied spectroscopically, a difficult task given their faintness, it could provide a chemical cross-section of an interstellar object, a treasure trove of information about conditions in its parent system. There is also the question of whether carbon dioxide dominance is familiar or foreign. Within our solar system, CO2-rich comets are unusual but not unheard of. A few display higher than expected carbon dioxide activity, particularly those that formed in intermediate zones of the early solar nebula between the water snowline and the carbon monoxide snowline. In such regions, water exists as vapor, but carbon dioxide can still condense as ice. If Atlas formed in a similar region around another star, then its chemistry, though extreme, may still be natural. But the scale of Atlas's CO2 coma complicates things. Observations suggest it extends hundreds of thousands of kilometers larger than Earth's diameter, larger even than the distance between the Earth and Moon. For such a small nucleus, sustaining so vast a cloud seems difficult to explain. Some researchers propose fragmentation, chunks of CO2-rich ice breaking away and sublimating as independent bodies. Others suggest interactions with the solar wind are amplifying the size of the cloud. Either way, the physics remain puzzling. And then comes the more speculative possibility that such trails could be engineered. If a swarm of probes wished to mask itself as natural debris, one method would be to release gases that mimic cometary behavior. A vast CO2 coma would serve as camouflage, hiding technological activity within what appears to be chemistry. It is a provocative idea, difficult to test, but it lingers at the edge of the conversation. For now, the jury remains out. The companions are too faint for detailed spectra, too elusive for certainty. They may match Atlas's carbon dioxide signature, proving kinship. They may differ, revealing hidden diversity. Or they may show nothing at all, fading into invisibility before we can measure. What is certain is that carbon dioxide trails, whether familiar or foreign, force us to confront our assumptions. Atlas has already broken the mold. If its swarm echoes that same alien chemistry, then the message is clear. Planetary systems elsewhere do not build comets as we do. If they differ, the story is stranger still, a convoy of chemically diverse bodies crossing our skies together. Either way, the carbon dioxide trails of Atlas and its companions remind us that chemistry is not just science. It is story, written in vapor, drifting across the void. When the first whispers of a swarm trailing 3I Atlas reached the astronomical community, one question immediately followed. Are they transmitting? For decades, the search for extraterrestrial intelligence, SETI, has been listening for narrowband radio signals, beams of energy that would stand out against the natural hiss of the cosmos. If Atlas or its companions were probes, wouldn't they try to speak? Yet as weeks of monitoring have turned into months, the results have remained the same. Silence. This silence is not surprising. The vast majority of natural objects, from comets to asteroids, emit no radio signals of their own. Their electromagnetic output comes only from reflected sunlight, thermal radiation, or charged particles streaming from their surfaces. To expect a comet to speak is unreasonable, but to hope that an artificial fleet might announce itself is a temptation that astronomers cannot resist. The SETI Institute, along with radio telescopes like the Allen Telescope Array and China's 500-meter aperture spherical telescope, FAST, has pointed ears toward Atlas's path. They have scanned across the hydrogen line, the waterhole frequencies, and other bands considered likely choices for interstellar communication. The result has been consistent. No narrowband spikes, no modulated signals, no obvious patterns that could be interpreted as artificial. Atlas approaches in silence, its companions trailing just as mute. There are many possible explanations for this. The simplest is that they are natural, and therefore silent by definition. If the swarm is simply debris, there is nothing to transmit. A second explanation is distance. Even if a probe were transmitting, its signal might be too faint for our instruments. Power fades with the square of distance, and an object tens of millions of kilometers away would require a transmitter far stronger than anything we use routinely on Earth to be heard. A third explanation is intent. If intelligence were involved, perhaps silence is the point. Stealth, after all, is a strategy too. It is also possible that we are listening in the wrong way. Radio waves are just one slice of the spectrum. An advanced technology might use lasers, neutrinos, or exotic particles as carriers of information. They might operate in frequency ranges we have not yet considered, or encode data in subtle modulations of natural emissions. To us, the swarm would appear quiet. To them, it might be buzzing with traffic. Astronomers caution against leaping to conclusions. The history of SETI is filled with false alarms. The famous WOW signal of 1,977 remains unexplained but has never repeated. Pulsars were once labeled LGM Little Green Men before we understood their natural origins. Fast radio bursts, now traced to magnetars and other astrophysical sources, were once candidates for alien beacons. Silence is not proof of absence, but neither is it proof of concealment. It is simply the default state of the universe. Yet the silence of Atlas carries psychological weight. Oumuamua was puzzling because of its motion. Borisov was comforting because of its ordinariness. Atlas, with its swarm, hovers between the two. If ever there were a candidate for communication, it would be this, a convoy of travelers passing close to our planetary neighbors. The fact that they remain mute sharpens the mystery. Perhaps the truth is simple. Atlas is a comet, its companions are fragments, and silence is all we should expect. Or perhaps silence is part of the message. Not every communication is spoken. Some are demonstrated through action, through presence, through the very choice of path. A silent swarm passing through our solar system could be less a broadcast and more a performance, a geometry written in space rather than words written in sound. For now, all we can say is this: Atlas and its companions approach without a whisper. No radio signals yet. Only faint light, faint chemistry, and faint suspicion. And sometimes, in science as in storytelling, silence is the loudest signal of all. Silence, in astronomy, is never empty. Sometimes it hides meaning. Other times it forces us to listen differently. The story of pulsars illustrates this perfectly. In 1967, a young graduate student named Jocelyn Bell Burnell was monitoring radio data from a new telescope in Cambridge. What she found was not silence, but a peculiar regularity, a faint blip arriving every 1.33 seconds, precise as a metronome. Natural sources were not known to behave this way. Stars flicker, galaxies roar, quasars hum, but none repeat with machine-like rhythm. The discovery was so baffling that the team jokingly labeled the signal LGM-1, Little Green Men 1. For months, the pulses defied explanation. Were they a beacon, a signal, an attempt at contact? If so, who had sent it, and why was it so regular? Eventually, the truth emerged. The source was not alien intelligence, but nature's ingenuity. A pulsar, the collapsed core of a massive star, rotating rapidly and sweeping beams of radiation through space like a cosmic lighthouse. What looked like artifice was, in fact, physics. The silence of intention was replaced by the voice of nature, speaking in a new dialect we had never encountered. The lesson of pulsars is twofold. First, that nature can mimic design with unnerving precision. To early observers, the pulses felt too orderly, too deliberate to be random. But in truth, astrophysical processes can produce patterns far more elegant than we imagine. Second, that silence itself can be misleading. Pulsars were not transmitting messages, they were simply behaving as collapsed stars do. The meaning was ours to project. This history hangs over every new discovery, including 3I Atlas and its swarm. When we see faint companions trailing behind, we might be tempted to label them a convoy, a fleet, a designed formation. But the pulsar story warns us. What feels like intention may be structure. What feels like communication may be coincidence. The silence of radio signals from Atlas does not mean absence, but neither does the presence of order mean intelligence. At the same time, pulsars also remind us that mystery is productive. The mistaken assumption of alien origin did not diminish the discovery, it elevated it. Pulsars turned out to be among the most important astronomical objects of the 20th century. They serve as precise cosmic clocks, as laboratories for extreme physics, as beacons for mapping gravitational waves. Their silence, once puzzling, became an unexpected richness. Perhaps Atlas offers a similar lesson. Its carbon dioxide dominance, its possible companions, its silence in radio bands all may someday be explained through natural physics we have not yet grasped. If so, the mystery itself will sharpen our instruments, refine our theories, and deepen our humility before the cosmos. In the process, silence becomes teacher, yet speculation cannot be dismissed entirely. Pulsars, after all, were once candidates for alien signals because they looked so much like communication. If the swarm of Atlas continues to display spacing, timing, or chemistry that seems too structured, the analogy may return. Just as pulsars became natural lighthouses, perhaps Atlas will reveal itself as a natural convoy, or perhaps it will resist neat explanation, remaining in the liminal space where silence keeps us wondering. The key is balance, holding open the door to extraordinary possibilities without walking blindly through it. The history of pulsars shows us how easy it is to project intelligence onto silence and how valuable those projections can be, even when proven wrong. Atlas may not be a messenger. Its swarm may not be a fleet, but like pulsars before it, it forces us to ask questions larger than the answers. Silence, then, is not absence. It is invitation. Pulsars taught us that lessons can hide in signals we misinterpret. Atlas teaches us that lessons can hide in signals we cannot yet decode. In both cases, the cosmos whispers the same truth. When silence speaks, it is we who must learn how to listen. The idea of a swarm is not new. Long before astronomers applied the term to comets and fragments, human beings knew swarms as a force of nature here on Earth. Locusts blackening the sky, flocks of birds wheeling in unison, schools of fish darting as one body, these spectacles etched themselves into our stories and survival. They were at once beautiful and terrifying, unpredictable, overwhelming, and greater than the sum of their parts. When we look at Three-Eye Atlas and its companions, we are, in some sense, seeing the cosmos mirror a pattern humanity has always known. In ancient texts, swarms carried symbolic weight. In the Bible, locusts were harbingers of famine and divine punishment. In Chinese chronicles, they were markers of dynastic turmoil. Indigenous peoples across the globe described animal swarms not only as ecological events, but as metaphors for community, power, and inevitability. To watch a cloud of insects or a flock of starlings was to glimpse order emerging from chaos, a natural intelligence without a central mind. Science later revealed that swarms obey simple rules. Each member follows local cues, keep close, avoid collisions, match speed. From these rules arises emergent behavior, patterns too complex to be commanded by any one individual, yet too structured to be random. This principle, known as swarm intelligence, has inspired everything from algorithms that route data across the internet to robotic systems that self-organize without central control. Human culture, it seems, has not only feared and admired swarms, but has also learned to imitate them. In the age of technology, the metaphor has expanded further. Armies have imagined drone swarms overwhelming defenses. Engineers design satellite constellations as orbital swarms, each unit contributing to global communication. Even traffic systems, in their way, operate like emergent swarms of vehicles responding to local conditions. The swarm has become a model for resilience, decentralized, redundant, unstoppable. It is here that the leap to the stars becomes natural. If humans already use swarms in war, communication, and exploration, why not in space? A single massive starship, like those imagined in science fiction, is costly and fragile. A fleet of thousands of smaller probes working in coordination is practical. They could spread across a solar system, each sampling a different niche, each relaying data back. Together they would form a net, a cosmic survey far richer than any solitary explorer could achieve. Writers and futurists have long anticipated this. From Arthur C. Clarke's visions of orbital swarms to modern concepts of breakthrough starshot, tiny, laser-driven craft launched in fleets toward Alpha Centauri. The idea of distributed exploration is no longer confined to fiction. Our own designs now echo the very strategies we speculate about when we see formations in space. Seen through this lens, the possible swarm trailing 3I Atlas feels less alien. It feels familiar. Humanity has always lived with swarms, feared them, harnessed them, and now begun to build them. The parallels make speculation almost irresistible. Could what we are observing be someone else's version of the same idea? A natural evolution of strategy, converged upon by different minds in different corners of the galaxy. Of course, nature still offers its simpler answer. The companions of Atlas may be no more than comet fragments, scattered by forces we already understand. But human history teaches us that swarms carry meaning, whether in the fields of ancient farmers or in the skies of modern engineers. They symbolize both vulnerability and strength, both chaos and order. So, when we watch Atlas and its faint procession of followers, we are not only studying astronomy, we are also looking into a mirror, seeing reflected back at us the oldest story of all, that in numbers, whether of locusts, drones, or starships, there is power, and that swarms, wherever they appear, remind us that intelligence may lie not in individuals, but in the patterns they create together. The swarm may be nothing more than random debris, a family of fragments cast out of a distant star system billions of years ago, traveling together by chance. Physics allows for this, and nature is full of such accidents. Yet, the way these companions trail behind 3I Atlas, the faint order in their spacing, the uncanny timing of their arrival, all of it forces us to pause. Are we simply witnessing coincidence, or does the appearance of coordination suggest something more? The beauty of astronomy is that it rarely gives us easy answers. Instead, it leaves us with questions that echo far beyond data and numbers. Tonight, as we follow Atlas and its silent procession across the sky, we are reminded that the universe is vast, unpredictable, and endlessly surprising. Whether debris or design, swarm or fleet, what matters most is the wonder it stirs, the quiet recognition that we live in a galaxy filled with stories we are only beginning to read.